All right, so let's look at the first question now. So what they say is we have a 3300 volt, 50 hertz, three-phase, star-connected induction motor with an output power of 100 kilowatts. Okay, so what is that output power? That is the power that is output by the shaft. Okay, so that's what we have left over after all these losses, the rotational losses, the copper and the iron loss of the rotor, and the copper and iron loss of the stator. So that's the available output power to turn a pump or a fan, okay, as an example. So that motor now has a synchronous speed of 500 revolutions per minute. So that's what the rotating magnetic field is rotating at, 500 revolutions per minute. The full load slip is 1.8%. So like we said in the previous video, the rotor cannot move at the same speed as the stator or the rotating magnetic field. It tries to, it speeds up and up and up, and it gets almost to the stator speed, but it has to be just slightly slower. And that percentage slower is called the slip. All right, so how much slower is this thing moving? So we say 100% minus 1.8 equals 98.2%. So the stator is moving at 100% speed, which is 500 RPM, and the rotor is moving at only 98.2%. So it's almost there, but it cannot reach there. Another way of writing that is 1 minus 0.018 equals 0.982. Okay, so it's 0.982 of the stator. Okay, so looking at the problem now, we got given, we need to continue reading. The power factor. The power factor is 0.85 lagging, and because it's an induction motor, it's full of windings, it's always going to be a lagging power factor. And now we have the stator copper losses over here. The stator copper losses, they said, was 2,440 watts, which is 2.44 kilowatts. The iron loss of the stator is 3,500 watts, which is 3.5 kilowatts. And then they say the rotational losses, remember this is friction and windage, they give it to us as one number. So that's 1,200 watts or 1.2 kilowatts. Okay, so now we look at the question, and they say to us they want the rotor copper loss. Okay, so the rotor copper loss. And the question also didn't give us the iron loss of the rotor. They didn't say anything about it. So therefore, we're going to just say it's zero or negligible, and it's unknown. So we're just going to ignore that. So the first thing we can do is we can calculate what the speed of the rotor is. And remember, it's going to be just a little bit slower than the stator or the rotating magnetic field. And we're going to say that the speed of the rotor equals 500, which is the synchronous speed, open bracket 1 minus 0.018, and that's going to give us 491 revolutions per minute, which is what we expect. So the stator is 500, the synchronous speed, and the rotor is slightly slower, 491 revolutions per minute. Okay, so that's the rotor speed. Now, we need the power copper loss of the rotor. Now, how are we going to get there? So we have the power output of the motor, and if we say the power output of the motor plus the rotational losses, we will get the rotor power. So the output from the rotor. Remember, the output from the rotor is connected to the shaft, minus the friction and windage gets the power out. So we're just working backwards. So the power out plus the rotational losses, so it's 100 plus 1.2 equals 101.2. So that's your rotor out. So that's this one here. Okay, so that's the rotor out. And then if we had the power copper loss of the rotor, we could just add that to the power rotor and we would get the stator power or the synchronous power. But we don't have that. I hope you would agree with me by just looking at this, that the power of the stator, the power that comes from the stator, must be greater than the power of the rotor, because the rotor has its own losses. So if we had the power of the copper loss of the rotor and we added it to the power of the rotor, we would get the synchronous power or the stator power. Okay, so if we just look here now, the power of the stator or the synchronous power would just be the power of the rotor out from the rotor over 1 minus the slip. And you'll see that is 101,2, which is the power of the rotor, which we calculated here, divided by 1 minus 0,018, which is the slip. So essentially that's 101,2 divided by 0,982. And you'll see that because we're dividing it by that fractional part of a number, it's going to get bigger. Okay, so you see the stator now has a power out of 103,05 kilowatts. So the power is increasing, and that's what we'd expect. All right, so now that we got the stator power, we can easily figure out what the rotor copper loss is. All we do is we say this number, okay, times by the slip. And so here I wrote here slip times the power of the stator or the synchronous power. So it's 0,018 times 103,5, and you get only 1,85499 kilowatts. So that there now is your copper loss of the rotor. So 1.85 kilowatts is what's lost in the copper. Another way you can do this, you can combine these two formulas together. So you can substitute the P rotor over 1 minus S into this here, and then you'll get this formula, and then you can just plug everything straight into that and just get it in one go, the copper loss of the rotor. All right, so that's the first part of the answer done. And then they say to us, what is the line current? The line current of the motor. And for that, we need to carry on going up the diagram. So we have the synchronous or stator power, which is 103,05. And if we add the copper loss of the stator and the iron loss of the stator, we'll get to the power N. Okay, and we want to know what the power N is, so we can know what the line current is. So there, I've done it over here. The P sync, it's done over here. It's the rotor power, which is 101,2 plus 1,855, and then you get 103,05 kilowatts. So that's your synchronous power. Okay, that's that one there, which we just worked out in the previous one. And then the power N is just the synchronous power plus the copper loss of the stator and the copper loss or the iron loss of the stator. Gives us 108,995 kilowatts. So you can see it's getting bigger every time. So there, the synchronous power plus those two gives us the power N. So now we have the power into the motor. Okay, with that, then we can go to the power formula, and we can say square root 3 V line, which they gave us, of 3,300 volts, times I line, which we're looking for, times cos phi. They told us what the power factor is, 0,85 lagging, and we calculated what the power N is. So this is power N, and that's 108,995, and then we get the line current. So that's the current that we are supplying to the motor, or that's the current that the motor is pulling from the supply. Okay, and then the last part of the question, we want to know what the efficiency of the full load efficiency of the motor is. And if we go back to the diagram, very easy. Efficiency is just power out over power in, and so it's power out over the power in, and we calculated what that was. It was 108,995 kilowatts, and we're just going to put 100 over 108,995 and get the efficiency of the motor. So there you go. So the power out over power in, and we get an efficiency of 91,7473%. So I hope that illustrates how to use the diagram for the problem. So you just you plug in the information that you get on the diagram, and then remember, be able to visualize what the shaft is. The shaft is physically fixed to the rotor. Okay, the shaft has its friction and windage losses. The rotor interacts with the stator rotating magnetic field. It can't move at the same speed as the synchronous speed because of slip. And yeah, so hopefully that helps you guys out.